And now it's time to focus on logic. So we're going to look at truth tables so that we can expand upon what we know about logic based on the previous lecture. We are going to state the truth tables for the 5 fundamental connectives. We're going to compute them. We're going to determine when they're logically equivalent, and we're going to state and apply De Morgan's laws. When we want to know if a pair of statements such as not PQ and not P and not Q mean the same thing. So a lot of times we want to distribute that not through and say, yes, it should mean the same thing. But in reality, in the real life, when we start putting in phrases into our logic or concepts, we need a truth table to really determine if compound statements are true and when they are false and whether or not they even have the same meaning. So if P is true, then not P is false. So if the sky is blue is true, then the sky is not blue is false. If P is false, then not P is true, like a double negative. So if the sky is not blue, the double negatives cancel out and we actually get that the sky is blue is true. It's a little tricky to think about. So we basically are going to complete this 4 square here with what P means and not P means in relationship to one another. How do we use this to make sense of the world around us? Well, if I'm trying to determine if each statement is true or false, and then I want to state this is a negation, we want to notice the change that happens in the phrase. So the Dallas Cowboys are a well-known football team. That's our statement. Mexico is a prosperous country in Asia. That's another statement, not necessarily true. So if I want to negate the Dallas Cowboys statement, I'm going to say the Dallas Cowboys are not a well-known football team is false. Because if that was true, then the opposite would be false. Mexico is obviously not in Asia, so that means that this statement is false. And so when I say not to negate it, that actually is a true statement. So it's really important to understand your starting point to know if you're actually dealing with a true statement or a false statement. A conjunction is only true when both parts of its components are true. So if you look at the red here, P and Q are true, and so P and Q are true together in the compound statement. But anytime there's a false involved, then I'm going to have a problem and my compound statement can't be true. So let's look at an example. We're going to work on finding those truth values in conjunctions. So J.K. Rowling is a well-known writer and U2 is a famous rock band. I have 2 different statements happening here formed with a conjunction. So in the English language, this is a compound sentence, and in logic, this would be a compound statement. And so if we just look at that first piece, that if J.K. Rowling is a well-known writer, well, that is true. And then U2 is a famous rock band, that's also true. Then from what we learned earlier, then P and Q are, the compound of P and Q is also true. So that means the entire statement of J.K. Rowling is a well-known writer and U2 is a famous rock band is true. And that should make sense. So if any part of the statement isn't actually true, then the compound sentence can't be true. And so look at this one. So in this one, Shaquille O'Neal played first base. We know that's not true. So straight off the bat, I know that's not true. So my compound statement is false. He refuses to do TV commercials is definitely not true. Depending on your age, you may not remember the hundreds of commercials that Shaquille O'Neal did. And the compound statement is false. Like we said earlier, if any one piece of it is false, the whole thing is false. When you're 50 years old, you will be a billionaire, and Maine is larger than California. Obviously, there are some different ways to interpret this. We don't really know if someone's going to be a billionaire, so there's not a concrete answer of whether P or Q is true or false. It's kind of going to depend on who's reading it. But we know that Maine is definitely not larger than California, so the compound statement is false, because if any piece of it is false, the entire thing is false. A disjunction is false only when both P and Q are false. That would be the bottom row. So notice we have a disjunction. Notice the V symbol is upright and not upside down. So what does that actually look like? So let's consider the ad. Management trainee wanted. So we're looking for a trainee. Applicant must have 4-year degree in accounting or 3 years of experience working in a financial institution. Which applicant would be considered? So I have 3 applicants that need to meet the criteria given in that previous statement. So Aya's background corresponds to line 2. The first statement is true for her, but the second statement is not true for her. But she should still be considered for the job, because that means that the inclusive PVQ is going to be true. So this is the difference in this table and the last table. The last table, if any one thing was false, and this time if only one thing is false, then the whole piece is true. So think about this like an or statement. I like bananas or candy. If you like either bananas or candy, it's a true statement. Heidi's credentials from here are not reflected in line 4 of the table. So if I look at her credentials, she studied accounting in college, but she didn't graduate college, and she's worked for 5 years selling electronics. So she is not going to be qualified because she falls into row 4, having met neither of the criteria. Monty's background corresponds to line 1, so he should be considered because he meets all of the criteria given, so he is a true statement. Because of their similar structures, there are some parallels between logic and set theory. So and is shown by the upside down V, or in the intersection for set theory. Or is shown by the V or the union symbol in set theory. Not is shown as the actual enye character, versus in a set, I use the complement. If then in logic is represented by an arrow, and it's a subset in set theory. So I use truth tables to find logical values of complex statements. The only thing a truth table does is it breaks something down into bite-sized pieces. So if I want to compute a truth table for this statement in that form, I'm going to have to follow a couple of steps in order to arrive at the final answer. I'm going to make a complete table that shows me the and the or statements for each of the situations, and then I'm also going to do the compound statement. And so if I look at this, if you remember, the and phrase is false if any one piece is false. The or means only one needs to be true. And then I would go from there into creating the other pieces of information. If the final column of a truth table contains all T's, then something is always true, and we call it a tautology, meaning it's always going to be true. How many lines should a truth table have? This is a great question. If the statement has k variables, then its truth table will have 2 raised to the k variables. So meaning if I have a compound statement with 2 statements, so like we given in the example earlier, the sky is blue and the sky is not blue, P and Q, 2 to the 2 is 4. So that tells me the truth table will have 4 lines. 2 statements are going to be logically equivalent if they have the same variables, and when their truth tables are computed, the final column is identical for all situations. So that means they all have to be true or all be false. So if I'm trying to determine if the statements are equivalent or meaning the same thing, I can look at the examples given on this page. So if I'm looking at the solution, if I let P represent the pasta bar accepts coupons, and D represent the deli accepts coupons, then I can write it symbolically as not P and D means that they will not accept. To decide whether these things are say the same thing, We're just going to make some truth tables, or you could even play it out with statements in your head. So because the final columns are identical for both situations, these statements are logically equivalent and therefore express the same exact information. So I made one truth table for P and D being true, and then one truth table for P and D being not true, or using that counter-contrapositive lingo. De Morgan's laws for logic implies that if P and Q are statements, then not P and Q is logically equivalent to not P and not Q. So this allows us to break them out. Instead of being in one compound statement, I can examine them individually. If not P or Q is logically equivalent to not P and not Q, then I'm able to also make some additional information. If I want to use De Morgan's laws to rewrite some statements based on the instructions of filing the 1040A tax form, it is false that you received interest from a seller finance mortgage and the buyer used the property as a personal residence. So that's the statement and the information we're going off of. It's easy to rewrite this statement if first we represent it symbolically with let R represent you received interest from a seller finance mortgage, and B represents the buyer used the property as a personal residence. The statement has the form not R and B. By De Morgan's laws from the previous page, this statement is equivalent to not R or not B, which we can now rewrite in English as you did not receive interest from a seller finance mortgage, or the buyer did not use the property as a personal residence. So in this example, we want to construct an alternate method to constructing truth tables using this piece of information. So we're going to construct a truth table for the compound statement below, which you saw as a previous example. So remember, we constructed a table by following the following steps: step 1, step 2, and step 3. This is an alternate way to construct your truth table. So notice that we have our truth table is two truth tables combined, and we have an extra piece for the notation that's being used and or between the two phrases. If I want to construct a truth table for this scenario, then I'm going to follow these steps and arrive at this answer. So you don't have to use this method. This is just an alternate method. I strongly relate to the first method we showed you at the beginning of the slideshow, but it's always good to have at least two different ways to look at something.